In this video, we're going to do an example of applying the monotone convergence theorem to show that a sequence defined by a recursive formula exists. So the problem says, let a1 be 1, and let a sub n plus 1 be the square root of an plus 3 for n greater than or equal to 1. Prove that the sequence an converges and find the limit. So for these kinds of questions where you have a recursive, the sequence is defined recursively, it's a good candidate to apply the monotone convergence theorem. And let's just recall what it says. It says that if you have there's really two different cases. Suppose that you have an increasing sequence. So let's say you have A1, A2, and the AIs keep increasing, and the sequence is bounded by some number L. Then the sequence converges to L. Oh, well, L is the least upper bound in this case. So suppose that you have a bounded above increasing sequence, then it converges. And in fact, it converges to the supremum of the set given by the sequence. Similarly, if you have a decreasing sequence like this, the AIs just get less and less, and it's bounded below, then that sequence converges to the infimum of the set given by the sequence. Remember, a sequence is not the same as a set, right? A set is a collection of points. A sequence is actually, technically it's a function where you have a first element, second element, third term, etc. Okay. So going back to the example that we have, let's try to apply the monotone convergence theorem. So first we want to decide whether the sequence is increasing or decreasing. And then we'll prove that it's bounded, and then we'll prove that it is in fact increasing or decreasing. So from testing some examples, right, A1 is 1. What do we get for A2? Square root of 1 plus 3 is 2. Then when we try A3, we get the square root of 2 plus 3, which is the square root of 5. So it looks like it's increasing. But we have to prove it. And we have to prove, in order to apply the monotone convergence theorem, that it's bounded above. Notice that if we can show that the sequence is increasing, we don't need it to be bounded below. In fact, they'll follow. If you have a bounded above increasing sequence, it's automatically bounded below. So you don't need to show that it's bounded above and bounded below. You just need to show, if you suspect that the sequence is increasing, which we do in this case, we just need to show that it's bounded above. So the first claim is that the sequence is bounded above. Well, to prove this, we usually want to have an actual upper bound. And the question is, how do we come up with the upper bound? I mean, if you look at some simple numbers, 1, 2, the square root of 5, at least from the first three numbers, it's not apparent that the sequence is even bounded above, right? It might not be bounded above if you just look at the first three numbers. And so usually to get an idea of what an upper bound could be, we so our scratch work, this isn't the actual proof. Okay, so I'll put a little cloud to indicate this is not part of the proof. The idea is suppose that we knew that it converges. So then the an plus 1 approaches some number L, and the an approaches some number L. Well, then you have L equals the square root of L plus 3. And then you can solve for L. So if you solve for L, we get L squared is L plus 3. L squared minus L minus 3 is 0. And I guess we could use the quadratic formula since we can't factor it easily. So L would be 1 plus or minus the square root of 1 minus 4 times A times C all over 2. So that's going to be 1 plus or minus the square root of 13 over 2. Now, what do we know about these numbers? So 1 minus the square root of 13 over 2 is negative. Now, are any of the AIs negative? No, right? They're all non-negative because the first one is positive, and then the AIs for I greater than 1 are the square root of something, and the square root is going to be non-negative. And so we suspect that the limit is actually going to be 1 plus root 13 over 2. So we suspect that what's going on is you have this first number a1, which is 1, a2 is 2, a3 is root 5, and then the numbers are approaching L, which is 1 plus root 13 over 2. So we could try to show that the AIs are bounded above by that, but since that number is hard to work with, let's just work with a bigger number. And, okay, if you, let's just work with L equal, let's just work with the bound 3, right? 1 plus root 13 over 2 is less than 3. So let's just try showing that AN, the sequence AN is bounded above by 3. Okay, I'm going to erase the scratch work, and then we can go to the proof. So let's try proving this. I mean, we're trying to show that, so the proof of this, right? So we want to show that for each n, an is less than or equal to 3. So what proof techniques might we try? We're trying to prove a claim for all integers n, positive integers n, and we have a recursive formula, so we should try induction, right? Let's try induction. So we'll use induction. And what's the base case? The base case is n equals 1, right? Well, in the case of n equals 1, a1 is 1, which is certainly less than or equal to 3. So that's the base case. And now we need to do the inductive step. So suppose, and okay, depending on how you're used to doing it, there's several ways to set this up. You could suppose that the statement is true for k and then prove it for k plus 1. Or you could assume that it's true for n and prove it for n plus 1. Let's suppose that it's true for a sub k. So suppose that a sub k is bounded by 3 above. So we want to show that a k plus 1 is less than or equal to 3. Well, we know that a sub k plus 1 is by definition, okay, and this is for k greater than 1, it's the square root of a sub k plus 3. Now, can you see how we can show that this is less than or equal to 3? So we have this, a sub k is less than or equal to 3, and so the inside is less than or equal to the square root of 3 plus 3. Well, 3 plus 3 is 6. The square root of 6 is in fact less than or equal to 3. And so that proves the claim, because we proved this proves the inductive step. And since we have the base case, we conclude that the sequence is in fact bounded above by 3. All right, so we do have a bounded sequence. It's bounded above. And now we need to prove, what's the second thing we need to prove? That the sequence is increasing. So let's just recall what that means. It means that A1 is less than or equal to A2, and A2 is less than or equal to A3, A3 is less than or equal to A4, etc. And a natural proof technique is what? Induction again, right? So we need to show well, what's the base case? So we'll prove this by induction. So the claim is that for all n, a sub n is less than or equal to a sub n plus 1, right? So the base case is the case of n equals 1. So the base case is to prove that a1 is less than or equal to a2. Well, so show that a1 is less than or equal to a2. This we can calculate just explicitly, because a1 is 1, a2 is 2, so a1 is less than or equal to a2. Check. Now what's the inductive step? So we assume that the statement is true for k, that a sub k is less than or equal to a sub k plus 1. We want to show that the statement is true for k plus 1, that a sub k plus 1 is less than or equal to a sub k plus 2. Well, why don't you take a moment and try doing that, and then we'll go over one possible proof. Okay, let's go over the proof. So a sub k plus, let's see. So we're assuming that a sub k is less than or equal to a sub k plus 1. We want to show that a sub k plus 1 is less than or equal to a sub k plus 2. And we know that a sub k plus 2 is defined in terms of a sub k plus 1. So we have a sub k plus 2 is the square root of a sub k plus 1 plus 3. And we're assuming, let's just write down what we're assuming, that a sub k is less than or equal to a sub k plus 1. That a sub k is less than or equal to, so a sub k is the square root of a sub k minus 1 plus 3. And we're assuming that's less than or equal to a sub k plus 1, which is the square root of a sub k plus 3. Okay. And we want to show that a sub k plus 1, which is the square root of a sub k plus 3, is less than or equal to the square root of a sub k plus 1 plus 3. This is what we're trying to show. Well, now do you see what we can do? Since a sub k is less than or equal to a sub k plus 1, a sub k plus 3 is less than or equal to a sub k plus 1 plus 3, and since these are all positive numbers, or at least non-negative. Well, once you add 3, you're going to get positive, right? For all I, the square root of a sub k plus 3, a sub k plus 3 is less than or equal to the square root of a sub k plus 1 plus 3. And this is equal, on the right, I have a sub k plus 1. On the left, I have a sub k. Sorry, I have a sub k plus 2 here, a sub k plus 1 here. So a sub k plus 1 is, in fact, less than or equal to a sub k plus 2. So I guess we could have, so this is like the scratch work. I guess we could have, once we wrote down what we wanted to show, we could have just skipped here, right? So we could just leave out this part. But, you know, it's a good idea to write down the scratch work of what you want to show, what we're given, etc. So that's the proof of the inductive step. So what we prove is that we do have an increasing bounded above sequence. And so what do we, so let's just call this claim 1. Let's just call this claim 2. By the monotone convergence theorem, the sequence a sub n converges. And that's the proof that the sequence converges. Now to find the limit, we let L be the limit of the an as n goes to infinity. So we know that we have an, okay, we have a sub n plus 1 is the square root of a sub n plus 3, right? For all n greater than or equal to 1. So you can take the limit as n goes to infinity of the left must be the limit as n goes to infinity of the right, since they're equal. And then the thing on the right is the square root, because you can distribute the limit across, of the limit as n goes to infinity of an plus 3. And the limit of a sub n plus 1 is the same as the limit of a sub n. So this is L equals, so this tells us that L is the square root of L plus 3. And then by the algebra that we did, we get that L is 1 plus or minus the square root of 13 over 2. But since the AIs are all non-negative, L must be greater than or equal to 0. So L must be 1 plus root 13 over 2. I guess it's more precise to say that L is 1 minus root 13 over 2 or 1 plus root 13 over 2, right? We're not saying that L is both of them. And since L must be non-negative, L must be this. So this is the limit. And what we wrote above is the proof that the sequence actually converges. Okay, so that's the answer. That's a complete proof to this problem. So let's just summarize what we did, because that took a long time. So first, since we have a recursively defined sequence and we want to prove it converges, even though the problem doesn't say to use the monotone convergence theorem, that's what we would probably try to use. First, we test some values to decide whether the sequence appears to be increasing or decreasing. In this case, it appears to be increasing. Once we have that intuition, by the way, it's obvious. If it's either increasing or decreasing, it's obvious from just A2 and A1 whether it's increasing or decreasing, right? Once you know which one it ought to be, then that shows whether we should prove that it's bounded above or bounded below. In this case, we have what we suspect is an increasing sequence, so we want to show that it's bounded above. And then to decide to prove that it's bounded above, we should actually try to find an actual upper bound. And what we did to come up with an upper bound was we assumed that the sequence converges and thought about what the sequence would converge to. And then we just pick a number that's bigger than that limit. Or we could, if the limit was simple, we could just use that limit. But in this case, the limit wasn't simple. So we just picked a number bigger, and then it's pretty easy by induction to prove, in this case, in this particular example, it's relatively straightforward to prove by induction that the sequence is bounded above by 3. Then, once you have that, we need to prove that the sequence is increasing, which we also proved by induction. And the base case is to show that A1 is less than or equal to A2. For the inductive step, it takes a bit of work to figure out what exactly to do to come up with the proof. But once you get used to it, it's not so difficult. I mean, this is relatively straightforward, right? The proof is like 2 lines. And then once we have that, we can conclude that the sequence converges by the monotone convergence theorem. And then to find the actual limit, so in this case, the problem asks us to find the limit, we just let L be the limit of the A sub n's, and then everywhere you see an AN or AN plus 1, whatever, you just replace that with L and then solve for L. In this case, there were 2 possibilities for L, but since we know that the AIs are non-negative, there's only one possible value for the limit. And that's an example of applying the monotone convergence theorem. There's no formula for doing this. I'm not saying that this works for every possible example, but this is like a general, this is the general idea of how to go about using the monotone convergence theorem to prove that limits of sequences that are defined recursively actually exist, and then how to find the actual limit. Okay, thanks.